Could black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works?
Imagine this: a silent cosmic monster lurking in the dark, a black hole so massive it weighs in at a jaw-dropping 400 million times the mass of our Sun. And yet, it doesn't roar, it doesn't glow, it hides. This game-changing discovery by the James Webb Space Telescope has just rewritten our cosmic playbook. But what exactly did Webb uncover? Why does this change everything we thought we knew about the early universe, galaxy formation, and the nature of black holes themselves? With its state-of-the-art infrared vision, the Webb telescope gazed into a galaxy from the ancient universe, a galaxy that existed less than 1 billion years after the Big Bang. In the heart of that young galaxy, scientists found the unmistakable evidence of a dormant black hole. Not just any black hole, but one of the most massive ever discovered from this early epoch. Unlike the bright, feeding black holes that light up space with powerful X-rays and radiation, this one was quiet, subtle, and almost invisible. So how do you find something that hides in plain sight? Astronomers used Webb's highly sensitive instruments to analyze the spectral signatures coming from the galaxy. And there it was, a gravitational fingerprint. The starlight didn't lie. The stars were moving in such a way that only an enormous, invisible gravitational force could explain it. No bright accretion disk, no telltale glow, just the eerie, unmistakable pull of a silent titan. Webb had caught the shadow of a sleeping giant. And this is where it gets astonishing. The black hole isn't just big, it's cosmically huge. 400 million solar masses. To put that in perspective, if our Sun were the size of a ping-pong ball, this black hole would be the size of a city block. Now here's the twist. This behemoth makes up nearly 40% of the total mass of its host galaxy. That's wildly out of proportion. In today's universe, supermassive black holes usually account for just 0.1% of their galaxy's mass. This black hole shatters that rule. That means something radical happened in the early universe. Did black holes form before galaxies? Did they grow first, with galaxies forming around them like cosmic scaffolding? Or was this a one-off anomaly, a freak of gravitational nature? Either way, it completely upends the old model of galaxies and black holes evolving hand in hand. And before we go deeper, take a second to subscribe. If you're fascinated by the cosmos, black holes, and the Webb telescope's groundbreaking discoveries, hit that subscribe button right now so you never miss a moment when the universe reveals another of its secrets. Now, let's dive deeper. This black hole isn't just enormous, it's practically asleep. Scientists estimate it's accreting matter at just 1% of the Eddington limit, the maximum rate at which a black hole can feed without blowing itself apart. This implies it may have grown explosively fast in the past, and now it's simply resting post-feast. But how could something grow so large, so fast, so early? One theory: super Eddington accretion. Picture a black hole in overdrive, swallowing gas and dust in an unstoppable binge, growing 10, 20, even 100 times faster than traditional physics would predict. Then, once full, it enters a dormant phase, quietly holding its mass as the surrounding galaxy evolves. But there's another, even more mind-bending possibility. What if this black hole was born massive? Some scientists propose that in the chaotic, dense early universe, massive gas clouds could have collapsed directly into black holes, skipping stars, supernovas, and the usual process entirely. These direct collapse black holes could instantly weigh in at millions of solar masses. If that's true, then we might need to reimagine the entire timeline of cosmic structure formation. Galaxies might not be the birthing grounds of black holes, they might be the aftermath. This discovery could also be the tip of the iceberg. Dormant black holes are hard to find precisely because they're so quiet. Active black holes blaze across the cosmos, but these silent giants hide in the shadows. Webb's ability to detect one suggests there may be countless others just like it, silently shaping the galaxies around them. And the implications go far beyond black holes. These findings may reshape our understanding of how stars form, how galaxies evolve, and even how dark matter and dark energy behave on cosmic scales. If black holes can form independently and dictate galaxy growth, then they aren't just passengers in cosmic evolution, they're drivers. Compare this discovery to others. The Gaia mission recently detected Gaia BH3, a black hole with just 33 solar masses, also dormant. But that's local, that's modern. What Webb saw is ancient, massive, and fundamentally different. It lived at a time when the universe was young, wild, and unstructured. And that raises a haunting question. What other silent giants are out there? What else is hiding in the invisible corners of the cosmos? With every observation, the Webb telescope is peeling back the curtain on the universe's hidden past. And this discovery proves that sometimes the most powerful forces in the universe aren't the ones that shout the loudest. They're the ones that whisper in the dark. Stick with us as we explore more groundbreaking discoveries, and remember, the universe is a lot weirder, wilder, and more mysterious than we ever imagined. Thanks for watching. Don't forget to like, comment, and of course subscribe for more journeys to the edge of space and time.